Hello everyone, we are moving on to thermochemistry. We did jump ahead to chapter 18 for our last unit due to the situation. So we're jumping back to chapter 17 and we're going to see some of the things that we saw in chapter 18, maybe even clarify a few of those things. But let's get into it. So thermochemistry is the study the interchanges that occur during chemical reactions and changes of state or changes of phase, so melting, freezing, boiling, all of those good things. Of course, it's just a little slice of overall of thermodynamics. So what is energy? Well, energy is ability to do work or produce heat. Okay. So there are many different forms of energy. There are two big forms of energy called potential energy and kinetic energy. Right? But you can see mechanical, electromagnetic, electrical, thermal, nuclear, gravitational, all of those things. But we are going to focus on chemical potential energy because, well, it's chemistry class. Okay. So chemical energy or chemical potential energy is just the energy that is stored in chemical bonds. So without getting too deep into it, when a bond is formed, we reduce potential energy. So chemical potential energy is the energy that is stored in chemical bonds. So when we break bonds and form bonds, there's energy changes, and that's what we'll be focusing on here. And so when we do this with the bonds, we can convert from chemical to mechanical, such as in your car. If you have a gasoline engine, we're turning that gasoline, taking that chemical potential energy, and through the process of the engine and things, we make the car go forward. We have chemical to thermal, which, let's say we're having a fire, we can feel the heat coming off of that as that chemical reaction proceeds. We have things like mechanical to electrical, so a motor or generator will take mechanical energy and convert it to electrical. But our focus here, the middle one, the bold one, is chemical to thermal. We don't do a lot of study on work in this class. So chemical to mechanical, the work process that can be done from a chemical reaction is not what we'll be doing. We'll really just be looking at energy involved in the chemical reaction, where it goes to, where it comes from, all of that. Let's see if we can change the slide. Okay. So heat. Okay. So heat is a key word. Okay. And heat is, of course, represented by the letter Q. Okay. We don't know why. Well, there's some explanations, but we don't really care. So heat is energy that transfers from one object to another because of temperature difference between them. So we're going to look at that a little bit closer. But one thing to note here is that heat is not something an object possesses, right? We don't say like your pencil has a lot of heat, right? It's going to have a lot of energy. It may have a lot of thermal energy. Heat is when that energy is moving from one object to another. Okay? So this is really a key slide. Okay? It really takes us to the foundation of thermochemistry or thermodynamics in general. Right? So if we look, we've got a little diagram here. We have, well, let's get a pointer up here. Let's see if I can change this to a pointer. So we've got higher temperature, lower temperature. Energy is going to flow. We call that energy heat. Okay? Energy is heat flow always moves from higher temperature to a lower temperature. That may seem foundational or easy or obvious, okay, but that is a key fundamental understanding. Okay? The other one is heat will flow as long as one temperature is higher than another. And this is going to lead to things that, right, eventually everything will come to the same temperature. Okay. So very, very important ideas. Energy is going to flow, or heat will go from higher object to lower, and that energy will keep going until the two objects reach the same temperature. So we've also got to look at a couple of words here. Okay, when we study energy changes, we define a system and the surroundings. Right? The system is just a part of the universe you want to focus your attention on. Right? One kind of thing we'll look at later is just ice cube melting. When we care about the ice cube melting, we're going to define the system as the ice cube. Okay? The surroundings are everything else in the universe. Now, we're not going to measure the entire universe, but we can look at the immediate surroundings. So if we put an ice cube on our counter, the surroundings are going to be the counter and the air around it. You could expand that a little bit, but we really only need to look at sort of the immediate surroundings. But technically speaking, the surroundings is everything else that is not defined as the system. Okay. The other is the law of conservation of energy. Right? And this states that in any chemical or physical process, energy is neither created nor destroyed. Which means if we know how much energy goes from one thing, we know that, or let's say leaves the system, we know that that amount of energy has to be absorbed by the surroundings. Now, how much each thing in the surrounding absorbs, exactly where it is, that's part of our measurements and part of this unit. Okay. Just another diagram down here. This is a higher temperature. Heat is going to flow there. And if this is the only two things we're looking at, we know that all the energy that object 1 loses is going to go to object 2. So we have another couple words. We used these terms in our last unit again. We kind of skipped this, so let's come back and make sure we understand. Right? In an endothermic process, the system gains heat as the surroundings cool. Again, it depends upon what you're going to define as the system and the surroundings. Right? If we take a fire, right? Now, if I am camping or something and I'm trying to get warm, right? Typically, I'm thinking I am the system, right? I'm trying to absorb some heat from the fire. So that is endothermic from the standpoint of me being the system. But in chemistry, we typically are going to focus the system on the chemical reaction, if there is one. So in this case, if we look at the chemical reaction going on, the fire itself is exothermic, right? Because the system, the fire, is giving heat to the surroundings. The surroundings are getting warmer. We're heating up the air. We're heating up the person, or at least the skin of the person. And so these terms are just defining heat flow relative to what the system is. So endo is into, so heat is flowing into the system. Exo is out, so energy is flowing out of the system. So just another picture to give us an example. Okay. If we take the contents of some chemical reaction and it heats up, right? We know it heats up because we feel, like, let's say the flask, we feel the air around it, it's getting hotter. That means the chemical reaction was exothermic. If we do another chemical reaction and we feel the flask and it's getting colder, that is going to be endothermic. Okay. And we'll talk about that a little bit more because this one seems to confuse people. And so we want to get into that a little bit more as we move through this unit. Okay. So kind of back to our ice cube example we were mentioning a little bit ago. So if we take the ice cube out of the freezer, what happens to the ice? Right? Well, since our focus is the ice, we're going to call the ice the system. So what are the surroundings? Well, as we mentioned, if you put it on the counter and the air, if I'm just holding it in my hand, the air in my hand would be the system. So let's say it's sitting on a counter, or just let's say it's in a glass. So the glass, the air around the glass, and maybe the counter because the glass is on the counter. All of those are the surroundings. So does heat flow from the ice to the surroundings? Well, I guess the first question is, we're also assuming this is our house, and so hopefully your house is above freezing. Right? So if it's warmer around the ice cube, okay, will heat flow from ice to the surroundings? Well, no. Right? Heat always flows from hotter to colder. So our choice is B. It's going to flow from the surroundings to the ice. So is melting process exo or endothermic? Okay, our definition of endothermic is flowing from the surroundings to the system. So we just said the heat was flowing from our surroundings to the ice. So melting is an endothermic process. We move on to a few more terms. These are our conversions, our units that we use. Right? So the measurement we use are the calorie and the joule. In science, we typically use the joule. Okay. Obviously, in food and things, we use calorie, although that's also a little bit confusing, which we'll get to in just a second. But the conversion is that 1 calorie is 4.184 joules. We can use our SI prefixes. So 1,000 calories equals 1 kcal. Okay. 1,000 joules is a kilojoule. But then we see this cal with a capital C. And so this big C calorie is actually what we see on our food labels. So when you see calories on whatever, here we see 25 calories. This is really a kilocalorie in terms of chemistry. So a food calorie and a chemistry calorie are different by a factor of 1,000. A food calorie is really a kilocalorie. So when you see your Snickers bar has 250 calories, that's really 250,000 chemistry calories. So keep that in mind. We'll try not to confuse you with this capital C. We try to point it out a little bit. It should have better terminology, but we tend to focus more in our chemistry class just on the chemistry calorie and the joule. So what is a calorie? Well, a calorie is defined as the amount of energy required to heat exactly 1 gram of water by 1 degree Celsius. Before we get into that a little more detail, this is another food label. A lot of foreign or other countries will use joules or kilojoules. This one is labeled with both kilojoules and kilocalorie. So if this were a US label, it would just say 61 calories. All right, back to our definition. So we're saying 1 gram of water. Okay, so how much is a gram of water? Okay. It's not a lot. Remember, it's 1 milliliter. 1 milliliter is 1 gram. So, and 1 milliliter is, we'll just draw a little box. It's pretty small. Not that that's trying to represent it accurately, but realize that, say, your typical water bottle you might buy is about 500 grams. Okay, and 1 degree Celsius. Okay. Well, if we wanted to heat that water up in your water bottle by only 1 degree Celsius, okay, that would take us 500 calories. So the unit of a calorie is not that large, right? Because, right, if we had water that we wanted to cool down to 0 degrees Celsius or ice water, so it came out of the tap at, say, around 20 degrees Celsius to make our math a little easier. We wanted to cool it down to 0, right? So that's a 20 degree drop. Well, we had 500 grams. 500 times 20. 500 times 20. That gives us 10, 1, 2, 3, right? 10,000 calories. Right? That we're going to actually have to remove from that water to cool our water bottle down to 0 degrees Celsius. So our next term is specific heat. Right? It's technically specific heat capacity, but most people just call it specific heat. And it's the amount of heat or energy it takes to raise 1 gram of a substance by 1 degree Celsius. It's already highlighted here, or circled highlighter, how easy or hard an object is to heat up. Okay? We may know or understand or observe that some things seem to heat up faster or slower than other things, even in similar situations. And that is all due to the specific heat. All right? Something with a low specific heat, like metals, are going to change temperature very quickly. Okay? Because it doesn't take a lot of heat to put in or take out to get a big temperature change. Right? So if I take just a pan, an empty like aluminum pan out of the oven, it's going to cool down really quickly. Right? But if I had a bunch of water at the same temperature, since it has a high specific heat, it's going to take a long time to cool down. Right? So metals tend to have a low specific heat. Water is something that has a very high specific heat, and because of that has some important properties that we will look at, or effects on our daily lives. Okay. So specific heat also not only depends on what the substance is, but what phase it's in. All right, so if we look at water, and here we're giving the units in joules per gram degrees Celsius. So let's look at that a second. All right. So these are the units of specific heat, because we said it's how much energy, so joule is energy, it takes to heat up 1 gram, so per 1 gram per degree Celsius, or 1 degree Celsius. All right. So our units are joules per gram degree Celsius. So for water, it's 4.18 or 4.184. Right? A number you will become familiar with because we use that number a lot. So it means it takes 4.18 joules to heat up 1 gram, 1 degree Celsius. Okay? So there are other units we could write here. Right? Well, we know we use both joule and calorie. So we can have calories per degree Celsius. So for water, the specific heat is 1 calorie per gram degree Celsius, because, well, we define the calorie essentially as the specific heat of water. Okay. So remember, we can convert from joule to calorie by 4.18 or 4.184. So joule per gram degree Celsius, calorie per gram degree Celsius. Right. We could put a kilojoule per gram degree Celsius, or whatever. It's just an amount of energy. The one big thing here comes from the fact that we know that if we go up by 1 degree Celsius, let's say we go from 20 degrees Celsius to 21 degrees Celsius, how much have we gone up in Kelvin? Okay, well, 20 degrees Celsius is 293 Kelvin. 21 degrees Celsius is 294 Kelvin. Right, so we go up 1 Kelvin. Right? It's the same, right? Because the Kelvin and Celsius scales have the same degree. Right? So if we go up 1 Celsius, we go up 1 Kelvin. If we go up 20 degrees Celsius, we go up 20 degrees Kelvin, or 20 Kelvin. So we could also write this as joules per gram per Kelvin. For water, it's still 4.184. Right? We didn't change that. So here, because this is a change in temperature, we don't have to do anything. Right? It comes back to these both are 1 degree. We just have the same unit. So you will see this unit maybe written or flipped around just at random, going, well, what happened to Celsius? How do we get to Kelvin? It's that they are interchangeable if we are talking about a change in temperature, and which is almost always the case in thermodynamics or thermochemistry. So while with gases we always had to convert Celsius to Kelvin, here, since we're looking at a change in temperature, right, in our calculations, we won't usually need to convert from Celsius to Kelvin. It's not wrong to do it. Right? If you're given Celsius temperatures, you convert to Kelvin, you'll still get the right answer as long as you convert correctly. Just we could see that there isn't actually the need to in most cases in Thermo. So kind of back to the point of this slide, we see that solid 2.10, many times you'll see it as 2.09. Use what's in front of you. The gas, a little bit more advanced, you may see some numbers like 2.02. Gas, it actually varies by temperature, but just we'll use the data that's in front of it. Our next term is heat capacity. Okay, heat capacity is the amount of energy needed to increase the temperature of an entire object exactly 1 degree Celsius. Now that might sound a lot like specific heat, but there is a big difference. Right? The difference comes in this fact that we say the entire object. Let me get my pen going here. So heat capacity is for a pure substance, okay, and it's per 1 gram of that. Right? So it's a property, kind of like density, of a pure substance. But when we talk about heat capacity, we're saying the entire object or entire sample. So if we have a pot of water on the stove, if we want just the water, that has a total heat capacity. We could also talk about the heat capacity of the pan and the water together. So the total system would now be the water in the pan. So that has a heat capacity. We can't say a water pan has a specific heat because it really doesn't make a lot of sense. Another way to think about it is like a cell phone. Right? If I, for some reason, put my cell phone in the freezer, right? We don't know the properties of that, but total, there's some amount of energy it's going to take to cool that phone down by 1 degree Celsius. We don't have a specific heat because it's made of like plastic and glass and metal and air trapped inside of there and other things. So overall, we could determine what the heat capacity of that object is through some experimentation, but we don't really have a property of a per gram because you can't cut off 1 gram of this and measure that and expect it to be representative of the whole object. So the units of heat capacity are going to be, you want to heat something up, or the energy needed, so joule. But remember, it's just heating that up 1 degree, right? So really the mass is taken care of when we talk about heat capacity. So if we can identify or given the heat capacity of something, right, we don't need to worry about the mass. Exactly, we just need to know what kind of temperature difference we're looking at, and we can determine how much energy that needs to heat or cool that up by a degree. Right. So these examples here are the kind of things where conceptually we want you to be able to describe and understand what's going on. So we're going to use this example and talk about a couple different ways we can interpret this. Okay. Our starting point is that specific heat about water is about 30 times larger than that of gold. Right? So H2O specific heat is much larger than gold. Okay. So if something has a larger specific heat, it's going to take more energy to heat that up. Okay. Or in other words, if we wanted to go from 20 to 90 degrees Celsius, we have to add 30 times more energy to the water than to the gold. And so if we were talking about kind of rates or how long it would take, assuming we put the energy in at the same rate, so same setting on a stove or put them both in same temperature oven, it's going to take the water about 30 times longer to heat up than the gold. Now, in heating and cooling rates, there's a little bit more to it, but as far as we're concerned, that's the basic foundation understanding. This also means it's going to take that much longer to cool down, or we have to remove 30 times as much energy from the water as we do from the gold. So if we're removing energy at the same rate, right, so we are heating them, let's say we turned off the heat sources. Okay. it's going to take water 30 times longer to cool down. Right? So the goal, and we'll just make up a number, if it took 5 minutes to go from 90 back to 20, it should take about 150 minutes for the water to cool down to the 20. Okay. Again, heat rates are not something we're going to get into, but that's a good approximation. We can also talk about just the amount of energy, again, is 30 times more for water. What this does for water is, and effects on our daily lives, are if we look at places that are close to water, like San Francisco, right, surrounded by ocean water that doesn't change temperature very rapidly, right? We're not going to measure a big temperature difference of the ocean water surrounding San Francisco on a daily basis. Yes, the temperature will vary throughout the year, and this isn't all that goes into weather and temperature, but the temperature in San Francisco is pretty steady throughout the day, right? And so you might see a 10, 15 degree temperature change from high to low temperature in San Francisco, whereas if you go to, say, Fresno, especially in the winter or summertime, you can see temperatures go from, say, 40, well, we'll call it 45 to 105 from morning to midday. And so that's a 60 degree temperature change, right? There's really no water around Fresno. There's not much water in the air. And while that all gets sort of a complicated analysis, it's kind of just one of the starting things to look at with the heat capacity or even specific heat of water. And if you look at like islands, especially like tropical islands, right, you'll see their temperature ranges from like 80 degrees Fahrenheit to 83 degrees Fahrenheit every day. Not a lot of change because they're surrounded by this massive amount of water, and that doesn't change temperatures very quickly. So that's our introduction to thermochemistry. In your book, you're going to read about math equations, and we're going to get to those next in another video. But for now, hopefully you've got some of the terminology, and hope this helped.
Have you seen Junior's grades?